Hello, today we are going to finish our conversation about alcohols, but before we get started, I want to show you this cool handout that's available right down there, right under where it says instructor's notes. You can download this handout and it has a summary of all the reactions we are learning this week. So all the alcohols reactions are in this PDF and it shows each row as a reaction and kind of gives it a reaction name and then gives an example, multiple examples of that reaction, what it looks like, starting materials, reagents, and products. There's also a column that tells you if you need to know the mechanism or not for the exam, so you should have those mechanisms handy if it says yes. If it says no, you never will be asked to provide a mechanism for that reaction. Also, you'll see that some solvents are highlighted in green. Those solvents that are in green mean if you accidentally leave it out on an exam, you won't lose points. So if it's highlighted in green, that means it's optional. But I will include it, so don't get confused if you see it. Those are just solvents. They don't do anything, they just are solvents. There's also a column called regiochem. Most of the reactions we've learned this week have no regiochemistry preference. We'll talk more about what exactly regiochemistry is next week, but it's things like Zaitsev's rule. So there's actually only one reaction in this whole handout that has an entry in the regiochemistry column, and it is the dehydration of alcohols reaction, which is an E1 reaction, and it says Zaitsev's rule, which just means that we're going to make the most substituted alkene. So don't worry too much about the regiochemistry column for now. And then finally, there's a stereochemistry column. If there's some details about the stereochemistry of the reaction, then it'll be mentioned here in this column, like inversion, racemic, things like that. It'll be there. Okay? All right, so check out this handout. It's an amazing practice for the exam. The only reactions actually that we've learned that are not on this handout are SN2, SN1, E1, and E2, and all of those reactions have their own handout. So aside from those four reactions, everything you need to know for the midterm 3 reaction-wise is on this handout. Okay, hopefully that's helpful for you. Okay, now there's some reactions on here that we haven't talked about yet, so let's talk about them. Let's finish off this conversation about alcohols. So yesterday, in yesterday's lesson, we talked about ways to make alcohols. And let me just quickly summarize that now. So summary of ways to make alcohols. And we saw 4 ways to make alcohols, 2 of which were old. So we could do SN2 to make an alcohol. If you took an R leaving group and you treated it with hydroxide in an SN2 reaction, you could make an alcohol. Another old way we learned to make alcohols, if you take R leaving group, usually this will be like secondary or tertiary, and you do SN1 with H2O, that's another way to make an alcohol. So we saw examples of that yesterday. Then the 2 new reactions that we learned involved using either organometallics or hydride reagents. So what we saw we could do was we could take an aldehyde or ketone and treat it with an organometallic like RMGBr or RLI. And this is going to create an alcohol and add an R group, a carbon group, to that carbonyl carbon right here. We also saw that we could use hydride reagents. For example, if we had the following substance, and we treated it not with an organometallic, but rather NABH4 or LiAlH4, we could turn the aldehyde or ketone into an alcohol. And so these are the 4 ways in this class that we've learned to make an alcohol so far. So 4 ways to make alcohols. I'll just say ROH. Now, today we're going to learn reactions that start with alcohols. So now once you make an alcohol, what can you do with it? The nice thing is a lot of these reactions are actually a review of reactions we've already seen before. So now let's learn what they do. As starting materials. Okay, all right, let's get started. The first class of reactions that alcohols can do are called oxidation reactions. And the first oxidation reaction that we're going to look at is something called PCC. PCC is a mild oxidant. I'll show you the structure of PCC down below, but let's first see what it does. And what it does actually depends on which type of alcohol you start with. If you have a primary alcohol, say for example ethanol, primary of course meaning that there is only one carbon attached to the alpha carbon, so there's, in other words, there's one beta carbon, and you treat that with PCC, the solvent, by the way, which is optional, is typically CH2Cl2, dichloromethane. The product of the reaction is an aldehyde. In other words, this is kind of like the reverse of sodium borohydride. So reverse of NaBH4, or the other hydride reagent, LiAlH4. And we can tell this is an oxidation reaction because we're going from something with oxidation state of 1 to something with the oxidation state of 2, because now there's a double bond to oxygen. So that's increasing the oxidation state of carbon, so this is an oxidation reaction. So PCC turns primary alcohols into aldehydes. The opposite of NaBH4, which turns aldehydes into primary alcohols. Okay, for secondary alcohol, PCC is going to do something similar. I'm not going to worry about writing the CH2Cl2. It's going to turn the alcohol into a ketone. So again, that OH group just turns into a CO double bond. That's what PCC does to secondary alcohols. And for tertiary alcohols, it actually does nothing. So if you try and take a tertiary alcohol and treat it with PCC, there's no reaction. And that's because it tries to make a CO double bond, but can't because there's already 4 bonds to carbon. So making the CO double bond would be like adding a 5th bond to carbon, which we, of course, is not allowed. By the way, you don't need to know this, but just for your curiosity, PCC stands for pyridinium chlorochromate. It's a highly toxic chromium-6 source. So this is a source of chromium-6. And it turns out that chromium-6 is a known carcinogen, very toxic. So largely PCC is being phased out, but it's still one of the most versatile reagents. You need to be very careful to use it because if you're exposed to the vapors or the dust, it can cause cancer. The structure looks like this. It's chromium with 3 oxygens attached, 2 CRO double bonds and a negatively charged oxygen, and then a chlorine also attached to the chromium. And then the counter ion, the spectator ion, is kind of funny. It's a pyridinium. So it's kind of like an ammonium counter ion. And that's the structure of pyridinium chlorochromate. I'll never ask you that. This is just for your curiosity for my advanced curious students, which I know you guys all are. Okie dokie, but you do need to know this, what it does to primary, secondary, and tertiary alcohols. Let's take a look at another reagent, Jones's reagent. It's also an oxidant, but it's a bit stronger. So this is going to be Jones's reagent. And Jones's reagent is formed when you combine chromium trioxide and sulfuric acid. Okay, it's a nasty freaking cocktail. The stuff will burn a hole right through you. You definitely don't want to get it near you because it'll oxidize you. Very scary stuff. And again, it's also a source of chromium-6, so highly toxic and highly corrosive. This is definitely considered a strong oxidant. You have to be really careful with this stuff. It's also bright red. It kind of looks scary. It's a liquid, nasty stuff. It's kind of similar to PCC, except the only difference is with primary alcohols. With primary alcohols, you treat that with Jones's reagent. And the combination is CrO3, H2SO4, and then the solvent is typically a mixture of acetone and water. I don't know why that has been the preferred solvent for this reaction. Seems a little bit strange to me to mix acetone and water. And then the product of that reaction is just like PCC, it's the aldehyde. So just like PCC, it makes the aldehyde, but it can't stop there. So although it makes an aldehyde, it continues reacting with the aldehyde to turn it into the carboxylic acid. So you can see this is quite a bit stronger than PCC. It takes an alcohol, which is oxidation state of 1, boosts it up to an aldehyde, which is oxidation state 2, but then boosts it up again to the carboxylic acid, which is oxidation state 3. So this is a super oxidation that goes 2 levels up. For secondary alcohols, it does the exact same thing as PCC and turns them into ketones. By the way, you don't have to write all of that CrO3, H2SO4, acetone, H2O. You can just write Jones if you want. And that does the exact same thing as PCC. It creates a ketone. So same as PCC. So that's nice. That's easy. And then for tertiary alcohols, also the same as PCC. It does nothing. So Jones. No reaction. Also the same as PCC. So the only difference is with primary alcohols, Jones's reagent will make a carboxylic acid, but PCC will just make an aldehyde. Okay, that's it for the oxidation reactions that we'll learn in this class for alcohols. The second reaction I want to show you is the acid-base reaction, and this is something we've already seen before. I know you guys have seen acid-base reactions before, but let's consider it for this part of the class because alcohols can participate in acid-base reactions. They can act as starting materials. So if you have an alcohol, it has a pKa of 16. So anything with a conjugate acid greater than 16 could potentially deprotonate an alcohol. One example of a very good base for deprotonating alcohols is sodium hydride. It's Na plus H minus, NaH. It's a very good base for deprotonating alcohols, and I'll show you the reason why. The product of the reaction is a sodium alkoxide, which is a deprotonated alcohol. So the sodium just sort of becomes the spectator ion for the alcohol now. And the product of the reaction, if you follow the arrows, look what the product is. The H minus grabs the H, which forms H2 gas. The H2 gas has a pKa of 36. So if you calculate KEQ for this reaction, you'll find that KEQ is equal to 10 to the power of 20, which is a very favorable reaction towards the products. Also, hydrogen gas is a gas, so it bubbles away. Little arrow to show that it bubbles away, and that drives the reaction even more towards the right side by Le Chatelier's principle, since the gas naturally removes itself from the reaction. So this is the only thing really new that we're seeing here is sodium hydride as a base. So, but really any base with conjugate acid greater than 16 will favorably deprotonate alcohols. Okay, and some new bases, some common bases that are used for this purpose we haven't really seen include butyl lithium, sodium hydride, that's what we just saw, and also sodium amide, NaNH2. So these three bases are very commonly used to deprotonate alcohols. They have pK of conjugate acid much greater than 16. So for example, this has pK conjugate acid of 50, 36, and 38. These things will just rip a proton right off of an alcohol to deprotonate it. Next reaction is one we've already seen before. And it's conversion of alcohols to halides. Or sorry, conversion of alcohols to tosylate. We'll talk about halides in a second. The tosylate group is the high-tech method. This is the high-tech method, a reaction we've already seen before. So we're just seeing it again because technically it uses alcohols as a starting point. And so if you remember this reaction, what it does is it takes an alcohol, and the reagents were tosyl chloride, TSCl, and pyridine. And then that replaced the OH group with an OTS group, which is a good leaving group. That's why we did this reaction. It makes a sulfonate leaving group, which is a good leaving group, and then you can do SN2 and all those things. But this is an example of a reaction that starts from an alcohol. And notice that the stereochemistry is unaffected. So if your alcohol was a wedge, it will stay a wedge when it turns into the tosylate. And I realize we are still just on reaction number 3. Okay, now time for reaction 4, which is conversion of alcohol to halide. And there's actually several ways to accomplish this, so I'll show them all. The first way is via the tosylate. As we just saw above, we can turn an alcohol into a tosylate, and then you could do SN2 on the tosylate with a halide salt. For example, take an alcohol and treat it with tosyl chloride and pyridine. Sometimes pyridine is abbreviated PYR. And that's going to make the tosylate. And then we can just treat the tosylate with a nucleophile and do SN2 or SN1. So we could treat it with, for example, sodium fluoride in DMSO solvent, a polar aprotic solvent. And that's going to replace our tosylate, which is a good leaving group, with F. So this is just SN2. Okay, another way is via the old school method, primary alcohol with HX, and we call this the old school method. Again, another reaction we've already seen before. This is a nice way to directly make a halide from an alcohol if you have a primary alcohol. You can treat it with HX, so for example, HCl, and you're just going to replace the OH with that halogen, in this case Cl, and it goes via an SN2 mechanism where first step is actually getting the protonated alcohol, and then the halide, like Cl minus, does SN2, kicking out the leaving group. So that's the old school method. We've seen that reaction before. And then just recently, a couple lectures ago, we saw that the old school method actually works with secondary and tertiary alcohols as well. But that it went through a different mechanism. Specifically, it went through the SN1 mechanism. So we could take, say, for example, a tertiary alcohol and treat it with HI. And that's going to create the iodide. And that goes via the SN1 process. So it goes through a carbocation intermediate. It's important to note that for B and C, this only works with HCl, HBr, and HI, not HF. If you want to turn an alcohol into the fluorine halogen, you have to use method A and do SN2. It doesn't work with HF for B and C. Okay, let's take a look at another reaction that can convert an alcohol into a halogen, one we haven't seen before. It's with a nasty, stinky reagent called phosphorus tribromide. It really is very smelly. So this reaction is reaction D. And this is methyl, primary, and secondary alcohols only. It does not work with tertiary alcohols. And the mechanism is essentially a double SN2. I'll show you the mechanism of this reaction. So if you take an alcohol, let's take the secondary alcohol here. And the conditions are PBr3, and the solvent is typically CH2Cl2. The product of the reaction is the bromide with inversion. And there's a byproduct of the reaction, which you don't need to write, but this is also produced. Let's take a look at the mechanism of this transformation. In the first step of the reaction, the alcohol acts as a nucleophile and attacks PBr3. So PBr3 is pretty electrophilic. It can be attacked by even a weak nucleophile like OH. So the phosphorus gets attacked, kicks out bromine as a leaving group. And that causes us to get the following structure. It basically turns the alcohol into a good leaving group, kind of like protonating it in a way. But then we also now have Br minus that we have in the solution because we just kicked it out with the PBr3 that does backside attack and kicks out this whole damn thing as a leaving group. So because it does backside attack, we flip the stereochemistry to the dashed. And we also kick out as a leaving group HO PBr2, which is our byproduct. So that's how this reaction works to convert an alcohol into a bromide. So this is an alternative to the old school method. If you want to immediately turn an OH into a Br, you can use PBr3. The nice special detail about this reaction is that it does inversion of stereochemistry. All right, next up is E. And for E, we're going to take a look at thionyl chloride. It's similar to PBr3, but it turns alcohol into a chloride. And this works again with methyl primary and secondary alcohol. And thionyl chloride has the structure SOCl2. Alrighty. Let's take a look at what this reaction does. Again, it's almost identical to D, in that it takes an alcohol. And the conditions for this are SOCl2 and triethylamine is required, ET3N. And the product of the reaction is a chloride with inverted stereochemistry. There are some byproducts of the reaction you don't need to worry about, but just for your curiosity. It generates triethylammonium chloride plus SO2 gas. And notice that just like PBr3, the product undergoes inversion. Okay, so this is a nice alternative to the old school method if you want to replace an alcohol with a chloride with inversion of stereochemistry. All right, those are all the reactions of ways to turn alcohols into halides, and really only D and E are the only new reactions we've seen so far in that category. Okay, next category. Reactions 5. This category is called conversions of alcohols to alkenes. We can turn an alcohol directly into a double bond. But the first method is actually more of an indirect way. We can turn OH into OTS. So turn the OH into a tosylate using the high-tech method, then do E2, since that makes a good leaving group. So for example, you could take this alcohol, you can treat it with tosyl chloride and pyridine to turn the alcohol into a tosylate group, and then treat it with a strong bulky base like KOTBU and just do an E2 reaction, eliminating away the leaving group. So that's sort of combining two reactions we've already seen before, the high-tech method and then just doing E2. There's another reaction we've seen before, the acid-catalyzed dehydration of alcohols. Which is an E1 mechanism. In this process, we are going to take an alcohol, and by the way, this only works with secondary and tertiary alcohols. So here's a secondary alcohol, and we're going to treat it with H2SO4 in heat. These are the E1 conditions, and the product is the alkene. Let's take a look at the mechanism of the transformation. In the first step, the alcohol gets protonated by sulfuric acid. So I will draw out the structure of the sulfuric acid. And so the alcohol acts as a base and gets protonated by the strong sulfuric acid to turn that OH group into a water group. So H2O plus. Then, just like in a typical E1 fashion, the water leaves to give a carbocation behind in a dissociation step. So in this case, we're going to get a secondary carbocation here where the water once was. And then a generic base is going to come by to take that beta hydrogen and eliminate it to give the alkene. So we've actually seen this reaction before at the, I think it was like 2 lessons ago when we were talking about E1 reaction. This is a possible E1 reaction starting directly from the alcohol. And it works because even though alcohol is not a good leaving group, H2SO4 is a strong acid, so it immediately protonates the alcohol to turn it into a good leaving group, water. Remember, our 5 good leaving groups are the same 5 leaving groups throughout the whole class. It's iodide, bromide, chloride, water, and sulfonates, like tosylate. All right, one more class of reactions, and that's all you need to know for the alcohol part of this class. And it's conversion to ethers. Okay, conversion to ethers. And we're only going to really see one way of doing that right now. We'll see another way to make ethers from alcohols, like I think next week, but let's not worry about that right now. And so this is going to be called the Williamson ether synthesis. And it's really surprises me that this guy, Williamson, put his name on this reaction because it's really just a SN2 reaction. So it's like not that special. Let me show you what it looks like. You take an alcohol, and it's a 2-step process. Step 1, you treat it with sodium hydride. You remember what sodium hydride does to alcohols? It's a strong base. It deprotonates them. So sodium hydride and the solvent is typically DMF. Then step 2, we are going to add something with a good leaving group so that that deprotonated alcohol can do SN2 on it. So for example, CH3Br, methyl bromide. Again, the solvent is DMF because this is an SN2 reaction, and polar aprotic solvent like DMF is really good for this reaction. And what's going to happen is our H on our alcohol is going to get replaced with whatever that substrate we added in step 2 is minus the leaving group. So if we use methyl bromide, we're going to add a methyl group instead of the hydrogen on the alcohol. Let's take a look at the mechanism of this transformation. As I said, it's a 2-step process. Okay. Step 1 is all about supercharging the alcohol. If you remember, alcohols don't do SN2. Alcohols are poor nucleophiles, so they make the SN2 column Na when you try and do an SN2 reaction with an alcohol as your nucleophile. So here's our alcohol, and it is a poor nucleophile. Okay? Then we're going to add sodium hydride, which is a strong base. And that is just going to deprotonate the alcohol in an acid-base reaction. And this gives us something called the sodium alkoxide, which is a strong nucleophile. It's a deprotonated alcohol. It's much, much, much more nucleophilic. So this is called the sodium alkoxide. And it's a good nucleophile. Okay, so the step 1, the sodium hydride, turns a bad nucleophile alcohol into a good nucleophile sodium alkoxide. And the byproduct of the reaction, of course, is H2 gas, which bubbles away, driving the reaction towards completion. And just to mention, NaH is amazing at deprotonating alcohols. It's pretty bad at everything else. So if you see NaH, you're probably going to be deprotonating an alcohol. Okay. Then in step 2, oops, we use the sodium alkoxide in an SN2 reaction. So now that we've made a super strong nucleophile, we can use it as a nucleophile in SN2. So here we have our sodium alkoxide. The sodium's just a spectator ion, it doesn't actually do anything. And then we add a substrate with a good leaving group. It should be a substrate that's not tertiary because we're going to do SN2 on it. So ideally it's either methyl or primary. Don't add, if you do secondary substrate or a tertiary substrate, it tends to do like E2 reactions instead. So just keep in mind this is an SN2 reaction like we've seen already. And so then what's going to happen is the supernucleophile is going to attack the alpha carbon in backside attack, kick out the leaving group, and then we're going to create the ether product, so the product of the SN2 reaction, plus sodium bromide is the byproduct, which is optional to write. Okay, so you can see that this guy, Williamson, he really just put his name on an SN2 reaction. The only real innovation here is using sodium hydride to first supercharge the alcohol, turning it into a good nucleophile, and then doing SN2 reaction, which is not a reaction he invented. So that's a nice little lesson in life, is you can just like piggyback on someone else's success, make a small change, and then sell it as your own. He was very good at marketing his reaction, and I'm sure he loves the fact that his name lives on. It's a legendary reaction, very popular reaction in organic chemistry, the Williamson ether synthesis. Okay, so that's all the alcohol reactions you need to know, and all of these reactions are summarized on this beautiful handout that you should see there on Canvas now. And you can see, like, for example, here's the Williamson ether synthesis, and you can see 3 beautiful examples of that happening. Here's the alcohol with PBr3. You can see that example as well. So check out this handout, and we will continue next time talking about synthesis. In particular, we'll talk about retrosynthesis. We'll talk about, if I give you a molecule that I want you to build, how you can go about stringing these reactions together to build my target molecule. Okay, bye for now.